ideal polyhedra in hyperbolic 3-space. And these words will make more sense as we go on with the presentation, so don't worry. So this is an overview of my presentation for today. First, we'll be looking at models that describe hyperbolic 3-space, and then we'll be looking at the purpose of my project in detail, and lastly, I'll be demonstrating a construction of a convex ideal cube in hyperbolic 3-space. So first, models of hyperbolic 3-space. So hyperbolic geometry has a different set of rules compared to Euclidean geometry, but today, instead of getting into the details of that, I'd like to just jump into models that describe hyperbolic 3-space to get a feel of what the objects in this space look like through these models. So the first one is the upper half space model. It's defined on the upper half of a 3-dimensional space. And hyperbolic lines in this model are vertical, half lines that are vertical to the complex plane or the boundary of this model. And also, lines are circular arcs orthogonal to the boundary, as you can see on the left. And hyperbolic planes are half planes orthogonal to the boundary, and also spherical caps orthogonal to the boundary. So this one is a semicircle, that one is a hemisphere, in other words. So lastly, and also very important, in this model, hyperbolic angles are the same as Euclidean angles. So the 90-degree angle you see in that picture is in fact representing a 90-degree angle in hyperbolic space as well. So this is the upper half space model. Okay. So the next one is the ball model. It's defined on the interior of a unit sphere. So it's inside the sphere. In this model, hyperbolic lines are spherical diameters and also circular arcs orthogonal to the boundary sphere. And hyperbolic planes are Euclidean planes that go through the center of the sphere, and also spherical caps orthogonal to the boundary. And in this model, similar to the previous one, hyperbolic angles are the same as Euclidean angles. So the two models we've looked at so far have really nice properties, and these are the only two we'll be looking at today. There are other models that describe H3. So after kind of getting a feel of what planes look like in the ball model at least, hopefully it's not surprising when I say this is a cube in the ball model. So it still sort of looks like a cube, right? So each of the faces are curved. That's because they belong to spheres. And also the edges, they're curved. I mean, the edge is also part of the sphere, but they're curved because they're circular arcs, right? Okay, so now we have some basic understanding of the models. Let's move on to the purpose of my project. So the purpose of my project was to partially answer to this question. Given a set of appropriate internal dihedral angles, how do we construct a convex ideal polyhedron in hyperbolic 3-space? So I know there's some terms that may not be clear at this moment, so we'll get into those. So what's a convex polyhedron? A convex polyhedron is a polyhedron such that when you pick 2 points in the polyhedron and draw a line that connects those 2 points, that line is contained in the polyhedron. It doesn't leave the polyhedron when you draw the line. And an ideal polyhedron is a hyperbolic polyhedron such that when it's in the ball model, all the vertices are on the boundary, as you can see in the picture. And also, some of you may have caught, I said, given an appropriate set of dihedral angles. What I mean by that is that we'll be dealing with a set of internal dihedral angles that belongs to a unique convex ideal polyhedron, up to isometries of H3. Now, what are isometries? Okay. So isometries are distance-preserving maps. So as a simple example, in Euclidean plane, isometries are reflections across a line, rotations, translations. Basically, it's not changing the shape of the object you have, right? Or changing the distance between the points, not changing the distance between the points in the set after you do the transformation. So now, let's revisit the question. Given a set of appropriate internal dihedral angles, how do we construct a convex ideal polyhedron in hyperbolic space? Hopefully it makes a little bit more sense now. Okay. So I'll partially answer that question through demonstrating the construction of a convex ideal cube in H3. So now, before I go any further, I'd like to clarify that I'll be using the word cube to mean cuboid. And what a cuboid is it's a polyhedron with the same combinatorial structure as a cube. That is, it has 6 faces, each consisting of 4 edges, and each vertex is incident to 3 faces. Okay, so I'll say cube, but I mean cuboid. It's like a generalization of a cube, sorry. Okay, so now I want to start my construction, but I had to decide which model do I want to complete the construction in. And my first 2 options were the ball model and the upper half space model, because they suited best to the purpose of my project. But which one do I want to use, the ball model or the upper half space model? And I ended up deciding to use the upper half space model because the calculation seemed a little bit more simpler. But although I had an idea of what a cube looks like in the ball model, because it still looks like a cube, I didn't know what the same cube would look like in the upper half space model, because the planes and the lines are defined differently. So how I solved this issue was by considering a transformation that takes the objects in the ball model to the upper half space model while preserving all the information. So you have a cube, and you have a cube, and there it's consisting of these spherical faces and lines. And when you use this transformation, it preserves all the lines, faces, and angles, and etc. So you're not losing any information. So one such transformation is a composition of Euclidean spherical inversion and planar reflection. We're not going to get into the details of this right now. We could at the end of the presentation if we have time. But in short, if we have a cube in the ball model that looks like this cube in the upper half space will look like that. Can look like that. It will look like this. Okay. So what happened was faces containing the vertex P became portions of vertical half planes, and the faces not containing the vertex P became portions of hemispheres. Okay. So now that we have an idea of what a cube looks like in the upper half space model, I want to proceed with my construction. But so far we only have this set of internal dihedral angles. We only have the information about dihedral angles. But I want to construct this whole shape. I want to know what these faces look, what the equation or the expression of these faces are, and where the vertices are, and so forth, given the information about the dihedral angles. So the approach I decided to take was to somehow, given the set of internal dihedral angles, determine the locations of these vertices that are on the complex plane. So how do I do that? So we have the internal dihedral angle information, information about the angles created by the surfaces, and I want to say something about what's going on the complex plane. So I proved some lemmas to do that. So if you have a dihedral angle alpha created by 2 half planes, vertical half planes in the upper half space model, then this angle alpha is equal to the angle created by these lines that are at the bases of the 2 half planes. These are equal, and that is because if you recall, in the upper half space model, hyperbolic angles are the same as Euclidean angles. So when you do Euclidean translation, these angles are equal. So if you look at the image in the middle, you have a dihedral angle alpha created by the half plane and the hemisphere. That's equal to the angle created by the tangent line at intersection of the base circle and the base line and the base line of the plane. And these are equal because we're just doing Euclidean rotation. And lastly, if we have a dihedral angle alpha created by the 2 hemispheres, then that angle is equal to the angle created by the tangent lines of at one of the intersections, or either of the intersections of the base circles. So after applying this knowledge, okay, we want to apply that knowledge. So let's say we had a cube in the upper half space that looks like this, and the internal dihedral, we had internal dihedral assigned as in the picture here. So all the y's are internal dihedral angles. To get into a little bit more detail, so the yellow ones are angles created by 2 vertical half planes, and the red ones are dihedral angles created by the hemisphere, portion of the hemisphere, and a plane. And the black one is the angles created by two portions of hemispheres. So if the angles are assigned as in the pictures on the left, all of that would show up on the plane, complex plane, as in the picture on the right, using the lemmas we just proved. Okay, so I'd like to note here that our goal right now is to determine the locations of the vertices that are on the complex plane. And so what do I mean by locations? So these internal dihedral angles gives unique convex ideal polyhedron up to isometries of H3. So without getting into too much detail, what that means is that we only care about the locations of these vertices up to Euclidean congruency. So we care about their location up to rotation, reflection, even dilation, translation, and so forth. So we don't care about those how that could change the shape of this. So what that means is that if we can find the angles that are consisting this image on the left, then we can determine, we only care about the angle information basically, I guess. So like if you have a triangle, you can make it bigger, expand it, or make it smaller. Up to congruency, they're the same thing. And the things that are not changing is the angles, right? So we only care about the angles. And so far, we know the three angles that are consisting this outermost triangle. So we know we basically know the locations of the points A, C, E. But at this point, we don't know the locations of the vertices O, B, D, F. So in order to figure those out, we drew additional edges, which are represented as the dashed lines on this image, and then assigned variables to the angles created by the dashed lines in the already existing solid edges. And then, looking at this picture and considering the relationship between the angles that are appearing here, we get this system you see on the right. And as you reduce that system, you get this simplified version, but we still have F as a free variable. And that shouldn't be the case. We should have a unique set of angles for A, B, C, D, E, F. Okay, so these are the angles we assign, A, B, C, D, F. And they should be a set of unique angles. So, but we weren't sure, after building this linear system, we weren't sure what the additional restriction should be. So we decided to just experiment with different set of A, B, C, D, E, F angles and found that this triangle FBD in the middle was not forming. And what I mean by that is that, okay, so let's say you knew the length of edge OF. Then by using these values of the angles, you can represent the length of edge. So first you can represent the length of OB using the length of OF and the sine of A and sine of B. And similarly, you can express the length of OD by using OB and sine of C and sine of D. So that means we can express OD with OF using the sine of these four angles. And you go around coming back to OF, then you can express OF using the original length of OF and the sine values of these 6 angles. And with that consideration, this relationship is true between OF and OF prime. And you might notice I used prime because when we start from here and go around, we want to just come back to the original length, but we don't necessarily because, well, this relationship is true. And if this value is not 1, the OF prime is not going to be, the length of OF we get at the last step is not going to equal the original length OF. So we're going to have this vertex F prime that shouldn't exist. So the last relationship we wanted A, B, C, D, E, F to satisfy was for this fraction to be 1, which is equivalent to this equation being true. So after solving that equation with the underline in terms of F, we get a unique value for A, B, C, D, E, F. So at this point, we have all the angles that are painted in red, which means we know the locations of all the vertices of the convex ideal cube up to isometries of H3. So now we're basically done. but I'd like to show you a realization of a convex ideal cube in the upper half space. So this is a set of internal dihedral angles for a convex ideal, unique convex ideal polyhedra in H3 that's been obtained from a different theorem. So to do the realization, until the previous slide we were talking about things up to congruency. So we need to set the locations of at least 2 vertices to actually realize it. So a convex ideal cube with these internal dihedral angles in the upper half space looks like this. This was produced through a code that I wrote. And the same cube in the ball model looks like this. And a little bit zoomed in, looks like this. Okay. So conclusion. So I also did a similar construction for a convex ideal octahedron. The steps were similar, so I didn't want to present. I also tried to do something similar with dodecahedron and icosahedron, but it didn't really work out. And that kind of relates to what I want to discuss in this section. So for the cube and the octahedron, the polyhedra were simple enough that this method worked out. But for dodecahedron and icosahedron, we have like more vertices compared to those smaller polyhedra. So we ended up having more free variables. So if you remember in the cube case, we had f as a free variable, and in the end we had to solve a nonlinear equation. So for polyhedra with more vertices, we might have more free variables and thus have more nonlinear equations. And we know nonlinear equations are hard to solve, so that could be an issue. So I'd like to thank the NSF for funding my RU, and I want to thank my RU mentor Franco, and thank you to Dr. Innermont for guiding me throughout my 6